In this lecture, we will be introducing the concept of a sequence. So we'll start with the definition. An infinite sequence, or just a sequence, of real numbers is an ordered list. And we write them A1, A2, A3, A4. The subscript tells you which term in the list we're looking at. We call A sub n the nth term. And notation, standard notation for a sequence will be A sub n in brackets. Or you may have A sub n in brackets where you have the index. This shows you what value is the beginning of the index to start the sequence and then how far it goes, in this case to infinity. And so again, the idea is it's just a list. Infinite sequence is just a fancy term for a list, an ordered list of terms. We can and often use functions to define a sequence. So if you have a function f of x, you can define your sequence by just plugging in the index to the function. And this is going to be the most common way that we define a sequence. So let's look at some basic examples. One sequence would be the sequence of 1 over n. So in this case, this would be the case of saying your function f of x is 1 over x, and if you plug in, say, 1, a1 is f of 1, or 1 over 1. a2 is f of 2, or 1 over 2. And you can think of the function 1 over x. If we look at the values when we plug in integers, we get 1, 1/2, 1/3. So these values are coming from the function 1 over x. You can think of the sequence as being tethered to it. You can also just think of this as, here's your formula, 1 over n. Start plugging in index values, starting with this initial value, 1. So you have 1 over 1. Then you increment it to 2. 1 over 2. Increment it to 3, a third, a fourth, going on forever. So this is one example of a sequence, a very classical sequence. We could also have a sequence defined like this, 1 over 2 to the n. Notice in this case, a little different. The index starts at 0. And it's important to recognize that your index can start anywhere, at any integer. So the way we defined it, we said we start at n equals 1. That's kind of the natural way to define it, with n equals 1 being the first term, index 1. But you don't have to start at 1. You can start at 0, you can start at 50, you can start at -3. It's arbitrary where you start it. It's just how you index your list. In the end, this is just a list. But we can start plugging in values and see. Plug in 0. 1 over 2 to the 0, which is 1 over 1, or 1. Then plug in 1. 1 over 2 to the 1, a half. Plug in 2. 1 over 2 squared, a fourth. Plug in 3. 1 over 2 cubed, an eighth. And you keep going. 1/16th, 1/32nd, 1/64th, so on and so forth. Another example, we could have something like this, where we have a power of n in the denominator. Notice in this case, you can't start with 0 because you would have division by 0. So sometimes the set of indices you can, or the starting value for your index is restricted because you can't have a division by 0. But in this case, if we start plugging in, 1 over 1 cubed is 1. 1 over 2 cubed is 8. 1 over 3 cubed, 1 over 27. 1 over 4 cubed, 1 over 64. 1 over 5 cubed, 1 over 125. And so on and so forth. So this is how we define sequences, typically. And again, it's important to remember a sequence is nothing more than an ordered list. We do have another way to define sequences, and we can define sequences recursively. The most classical recursively defined sequence is the Fibonacci sequence. And so the way this sequence starts is by giving initial values. So we say A naught is 1 and A1 is 1. So we have kind of hard-coded the first two values. After that, for n equals 2, 3, 4, and beyond, we say the nth term is the sum of the previous two terms. So let's take a look at how that works. A2, per that formula, would be so A2 would be A2 minus 1, or A1, plus A2 minus 2. And we see these initial values of 1 and 1 we can plug in, and we get 2 for the second term. So we have A naught, A1, A2 up here. Using that same recursive formula, and recursive just means it's defined by previous values of itself. A3 would be A2 plus A1. Come back to our list. A2 was 2, A1 was 1. So we get 2 plus 1, or 3. Similarly, A4 is A3 plus A2. A3 is 3, A2 is 5. A5 would be A4 plus A3. 5 plus 3 is 8. And we can keep writing the formulas out here, or you could actually look at this list and see the way to get the next term is to add the last two. So 5 plus 8, 13. 13 plus 8, 21. And this is, again, it's a classical sequence, the Fibonacci sequence. And it's the classical recursively defined sequence. And we'll look a little bit more at how you deal with these types of sequence when we get into sequence convergence. But it's also kind of a cool sequence because it comes up in nature. The most famous way that it comes up is in terms of counting pairs of mating rabbits. But Fibonacci sequence shows up quite a bit in nature. Now that we've defined sequences, really the question will become, what does a sequence look like as you march down the line? So as you go down the line here, is your sequence getting closer and closer to some number? You've studied this already when you considered the idea of a horizontal asymptote of a function. So remember, the idea of convergence for a function to an asymptote was this idea that you're getting arbitrarily close to this horizontal asymptote. So if we called that y value, say L, this would be where we had y equals L is a horizontal asymptote of f of x. Mathematically, that was because the limit as x goes to infinity of f of x was equal to L. And we want to define in a similar way the idea of a sequence getting arbitrarily close to this kind of number. And the way we can think of that pictorially is, let's just look at index values. So if we have our sequence, just imagine our sequence is tethered to this function. So we're drawing this in a way where a sub n matches this function f on the counting numbers. And we want to define what it means for our sequence to get arbitrarily close to L as we go down the real line in the positive direction. So our goal is to define what it means for the limit as x goes to infinity of our sequence a sub n to be equal to L. And again, this would be our A1, our A2, A3. So the idea being, as you go down the line here, these AN values are working their way up to L and getting arbitrarily close to it. And so that will be the next lecture. We will formally give the definition of sequence convergence and try and dig into those details.